Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of arithmetic sequences. If you don't know what that is, please rewind. Look at the last video. It's a whole introduction to arithmetic sequences. And if you don't know what a sequence is, rewind even further to watch the video on sequences, or the videos on sequences that I have up in my pre-calculus playlist. But for now, let's go ahead and tackle partial sums of arithmetic sequences. If you don't remember what a partial sum is, I should probably mention that. You need to watch my video on partial sums of a sequence and summation notation. I have 3 videos in a row that are all about partial sums and sigma notation and using sigma notation. So it's very important that you know that stuff, but without further ado, let's go ahead and jump into this. Partial sums of arithmetic sequences. Why are arithmetic sequences so awesome? Well, it's because they're one of the very few sequences that we can find out a formula for their partial sums. Now, I don't know if you noticed it in the previous video on partial sums, but when we were looking for what's S1 and S sub 2 and S sub 3, we couldn't really develop a formula. It's very, very difficult. And in practice, especially when you get to Calc 2, you'll find out very quickly that finding a formula for the nth partial sum, the sum of the first n terms of your sequence, is almost impossible. Yet there are 2 really common styles of sequences that have closed forms for their nth partial sums. And one of those is for arithmetic sequences. So, given an arithmetic sequence, remember I write them, actually I don't write them that way. I technically write them as a sub n is equal to d times n minus 1 plus a, where d is a common difference and a is the initial value of your sequence. The nth partial sum is given by either of the following formulas. So notice there's some patterns within this. The first pattern is the following. So if you look at the first formula, it almost looks like you're just taking half, in a way, it's not really, but of the original formula. Of course, the original formula doesn't have 2 of those a's there, but it looks like you're doing that. So it has your formula, but twice the initial value is there, and then you multiply that result by n over 2. The other way to see it, and this is kind of the way that I like to think about it, it's n, let me write this out, it's n times the average of the first and nth term. There we go, it's n times the average of the first and nth terms. Remember, when you average things, you add them up, divide by 2. So that's really what that is. But why is that true? That's really what you should be asking. Why is that true? Rather than just memorizing. Why is it true? So let's go ahead and prove that. Let's prove that the nth partial sum of an arithmetic sequence is that. Both of those, by the way. We're going to do both of them. So we'll start, I'm going to zoom in, by assuming we have an arithmetic sequence. So let's let a sub n be equal to a plus, I'll write it the way I want to write it, d times n minus 1 plus a. Okay, that's our arithmetic sequence. Well, if that's our arithmetic sequence, then S sub n, adding up the first n terms of this arithmetic sequence, is going to be a1 plus a2 plus ... down the line all the way to a sub n. That's by definition of an nth partial sum. You're just adding up the first n terms of your arithmetic sequence. That should not blow your mind. But now I could say, you know what that's equal to? Well, a sub 1 is just a plus Maybe I'll use black inked. So a sub 2 is a plus the common difference d, plus a sub 3 is a plus 2 of those d's, right? Every single time that you go to the next term in line, you're just adding another d. That's the whole point of the common difference, is that every step of the way, you're just adding d to the output. So the black a is the very first value. The green a plus d is the second term. The blue a plus 2d is the third term, or a sub 3. And you can keep doing this all day long. So plus dot 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 until you get all the way down to the nth term. And we know the nth term is going to be, let me put it in brackets, it'll be a plus n minus 1 times d. I know I wrote it opposite of what I write here. That's fine. It doesn't really matter. Okay, I'm just kind of copying a being first. It's kind of nice. All right. So what does that mean? Well, to really get you into this proof, to get you to believe what I'm doing, I'm going to actually extend this out a little bit. Let's suppose that we kept going and we got all the way down to the nth term, which is again a plus how did I write it before? A plus n minus 1d. Is that how I wrote it? Yeah, I think that's right. Well, the term prior to a plus n minus 1d was, I'll write this in blue, a plus n minus 2d. That's just the term right before the n minus first term would be the n minus second term. Okay. And of course, I could technically extend backwards a little bit further, and I could say, well, the term right prior to that was, well, I have dots there, so that's good. A plus n minus 3d. Okay, so again, let's say, for example, pretend n was 20. Then we start with a, then a plus 1d, then a plus 2d, a plus 3 plus 4 plus 5d plus 6d plus 7d, all the way until you get to plus 17d plus 18d and then plus 19d. That's all I'm saying. That's just saying that I'm summing up. I've just listed the first 3 terms, so I'm listing the last 3 terms. Of course, if that's what s sub n is equal to, you know that if I wrote 1 plus 5 plus 8, that you could write that as 8 plus 5 plus 1, right? So I'm going to show you a little trick in mathematics. This trick works very often for weird proofs involving sequences or summations of numbers. It is a really cool thing to do. So watch how I do this. I'm going to go ahead and rewrite this s sub n in the opposite order. That is, I'm going to grab this guy and write it first. A plus n minus 1 d. And then plus, I'll grab this guy and write it next. Let's see, a plus n minus 2 d. And then I'm going to grab this guy and write it next, plus a plus n minus 3 d. And so on and so forth down the line until I get to that guy right there. So I'll write that in blue. A plus 2d plus next guy in line, which is this guy right here, in green, a plus d, and finally plus a. And that should not blow your mind. I just wrote it in the opposite order, right? Nothing really too crazy there. But now watch what I'm going to do. If I grab these first 2 terms and these things and I add them up, so I'm adding 2 equations. So really that's what I'm saying I'm about to do. I'm going to add these 2 equations up. Then the left-hand side will become 2 of those s sub n's. That should make sense. On the right-hand side, the highlighted piece right here, a plus that business, becomes 2a plus n minus 1 d. I hope that's okay with you. Now, let me move on to the next two that I'm going to highlight. This one and this one. I'm going to add those two together. Well, let's see what I get. Plus a is 2a plus d plus the quantity n minus 2 d and quantity. Okay, not too terrible. So far, so good. Now I'm going to go to the next group, this one and this one. And let's see, when I add those two up, I get, again, two of those a's, that's kind of convenient, plus 2d plus n minus 3d. Go ahead and erase that highlight. Let's take a look at what we're looking at right now. And I'll continue doing that all the way down the line, plus, plus, plus. And then let's see, where do I pick back up? I pick back up right here. This guy added to this guy. Well, lo and behold, I get 2a's plus 2d plus n minus 3d. Okay, well that's kind of interesting, I guess. And let's see, where am I at now? I'm going to add this guy to this guy. And I still have room on my page. That's good. So plus, let's see, I have an a plus a, so that's 2a again, plus d plus n minus 2d. So far, so good. I feel very good about this. I'm going to erase those two. And the last one, I'll add this guy to this guy. And when you do that, you get, again, plus, I have two of those a's, plus n minus 1d. And you say, why did you go through all of that? That's just an absolute mess. I hate you for doing that. Whatever you say, I have no idea what you actually say. But I did it because if you look at this, this will imply that we have 2s sub n is equal to 2a plus n minus 1d in that first group. In the second group, let's see, I have 2a plus d plus n minus 2d. If you think about your mathematics here, you can factor a d off of that and you'll be left with 1 plus n minus 2, or in other words, n minus 1. And so that can be written as, I should have written it up above. This is d times 1 plus n minus 2. There we go. And that means that we have 2a plus n minus 1 again, d. Oh, that's interesting. Well, let's move on to the next one. Plus, I have yet again a 2a. And again, if you were to say, well, let me factor out a d off this group, I'm left with 2 plus n minus 3. But that's n minus 1. Huh, that's another n minus 1 times d. So far, so good. Plus, dot, dot, dot. Plus, this is 2a. Again, this group right here, I could factor a d out of, and I'm left with 2 plus n minus 3, or in other words, n minus 1 d yet again. Plus n minus 1 d yet again. This last, or second to last group, again I have a 2a, and again, these two, I could factor out the common d, and I'm left with 1 plus n minus 2, or an n minus 1 d. So again, plus the quantity n minus 1 times d. And finally, plus 2a, plus the quantity of 2a times n minus 1 d. Let me zoom out. Notice that's a bunch of 2a's plus n minus 1 d's. In fact, how many of them do we have? Well, we have as many as we have of these terms right here. That's where they were born of. So there are n of those. So I'm going to just say, zoom out totally here so I can see it all. I'm going to say, maybe in green, that I have n of these, n times. Well, if I'm adding a number to itself n times, that can be compressed down to be n times that number. And now divide both sides by 2, and you get the wonderful formula that we now know the summation up to the first n terms of the sequence will be n over 2 times the quantity 2a plus n minus 1 times d. That is the proof for that first formula. The second formula, actually, I'll leave it to you to prove. It's not actually too terrible. All you need to know is what a sub n is. And a sub n is a plus n minus 1. Actually, I am kind of proving it verbally. If a sub n is a times n minus 1 times d, then I can borrow one of these a's and this plus n minus 1 d, and I could trade that out for an a sub n. So I'll have an a, because I only borrowed one of them, plus a sub n. That's a quick, very fast proof of that. Very, very nice way to prove that theorem. So I'll write QED. It's a beautifully proved theorem. Quod erat demonstratum. So it has been demonstrated. Now let's use it. So let's see. Find the sum of the first 15 terms of our sequence. Given that the second term of our sequence is 8 and the fifth term of our sequence is 9.5. Oh, and by the way, didn't state it here, but this sequence should be arithmetic. So let me write that down. All right, so that's written down. Let's go ahead and figure out how to do this. I'd really love to use our newly found formulas. So let me go ahead and take a look at them. S sub 15 would be 15 over 2 times 2a plus n minus 1 d, right? So there's a lot of things going on here. I almost always just use this one. A plus a sub n divided by 2, so the average of the first and last term divided by 2 times the number of terms you're looking at. The reason why I like that is just because it's easier to remember. So this tells me that I need to find what the formula is, what the common difference is, all that fun stuff. So I need, in either case, honestly, D and A. I need to find out what the initial value is, and I need to know the common difference. Luckily, I've been given 2 points. I've been given the point 2, 8 and 5, 9.5. The output is 9.5 when n is 5. The output is 8 when n is 2. And so therefore the common difference would be the slope between those 2 points. Again, arithmetic sequences are linear in form. So let's see, 5 minus 2. So I have, what is this, 1.5 over 3. I think it's a half. So our common difference is a half. Great. Now I know, therefore, that our formula will be 1/2 n minus 1 plus the initial value. Notice I'm just doing what I did in the last lecture video, which is find the formula. It's just much more helpful when you do that. And you can use either of these 2 points here to find out what the initial value is. I'm going to go ahead and, let's see, I'll go ahead and use the 2, 8. So 8 is equal to 1/2 times 2 minus 1 plus a. Or in other words, 15 halves is equal to a. Let's see, 16 halves, 1/2. Yep. So this tells me that my formula for my sequence is going to be the common difference, which is 1/2 times n minus 1 plus 15 halves. And if I want to sum up the first 15 terms, you could choose whichever of those 2 formulas you want. I happen to use the averaging one. It's n, which is 15, times the average of the first term and the 15th term. That's just easier for me to remember, honestly. So much easier to remember. I'll pull that 2 out front. I'll just call it 15 halves here. The first term is 15 halves, actually, because of this. And the 15th term, I just need to compute that. A sub 15 is equal to 1/2 of 14 plus 15 halves. That's 7 plus 15 halves. And if you don't know how I got that, by the way, it's just from this formula. I just want to know what a sub 15 is because I'm averaging the first and the 15th term. And so let's see, 7 plus 15 halves, that's 14 halves plus 15 halves is 29 halves. 29 halves. A lot of halves going on this, right? Well, you either have or you have not. All right, anyway. So let's see. This is 39. This is 44 halves or 22. So 15 halves, 22. Let me just double check my math. 39 plus 5 is 44. Divided by 2 is 22. 2 goes into 22 11 times. So it's 15 times 11. That's 150 plus another 15. That's 165. Then what the heck did I just compute? Oh, that's right. I computed the sum of the first 15 terms of that sequence. Rather than me having to add up all those terms, I have a formula for it. That is the sum of the first 15 terms. A1 plus A2 plus A3 all the way to A15. Very nice. And remember, it always boils down, at least for me, to finding the formula of the sequence. Once you have the formula of the sequence, you have everything you need. So let's go ahead and do a fun one. I like these. These are really cool. On exams are great because I know if somebody's going to cheat, because normally I don't allow calculators. And so I know somebody's cheating when they sit there and say, I ran out of time because I was typing this all in. You don't have to type this in to find out the sum of this series of numbers here. You just have to write it as a sequence. The sequence is negative 10 is a sub 1, and a sub 2 is a negative 9.9, and a sub 3 is a negative 9.8, and a sub, you get the idea, right? Dot, dot, dot. Okay. All the way down. Actually, I should put the dot, dot, dot down and just call this negative 9.7. But the difference, every single time I'm adding a 0.1. I'm adding a 0.1, and so on and so forth down the line. So I know my common difference is 0.1, and I know a sub 1, which is a, is negative 10. I have everything to state the formula for this sequence of numbers. It's not actually a sequence of numbers, by the way, but when you write it out term by term, like I did here, it is actually a sequence of numbers that I want to add up. I want negative 10 plus a negative 9.9 plus a negative 9.8. That's really what I want here. I want to add up all those numbers all the way down to negative 0.1. So the formula that I'm looking at for my sequence that I'm using will be D times n minus 1 plus A. And A is negative, so it's minus 10. You could double check that this is correct. Let n equal 0. Or I'm sorry, 1, let n equal 1, and you will get 1 minus 1, which is 0, plus a negative 10, or in other words, negative 10. Now, I'd like to add up a bunch of values, right? I want to know what the sum of the first bunch of values are. I'm putting a question mark there. Sorry about that. Just didn't work out for me. So I want to know how many of these terms am I going to add up? Well, you can either use logic, or you can use the formula. The logic here is you have 100 terms you're adding up. So if you think about it, you have 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, all the way to 1, that's 10 terms. And then you repeat it from 1.1 to 2, that's another 10, and so on and so forth. And you have 10 of those 10s, which is 100. Or if you don't like that as a reason, then I'll just say, hey, when is a sub n equal to a negative 0.1? That's another way you could do it. And then you could solve. Oh, it's a negative 0.1 when 0.1 times n minus 1 minus, when it's equal to a 0.1 times n minus 1 minus 10. Okay, we'll add 10 to both sides. You get 9.9 is equal to 0.1 times n minus 1. Divide both sides by a 0.1. You get 99 is equal to n minus 1. Add 1 to both sides. And you get the 100 that I said it was going to be at. So, I want to add all 100 of these numbers together. Oh, that was me hitting my microphone. Sorry about that. So the question really is, what's S sub 100? That is not going to be a crazy question. Because remember, it's just the number n times the average of the first term in your sequence and the last term in your sequence. And technically, I didn't even need to write out the formula. I didn't need this formula here at all. All I really needed to know was that there are 100 terms here being added. And if that's the case, I'd say I started at -10. I end with the 100th term at -0.1. I want to average those two and multiply it by the number of terms I'm adding up. A very, very cool problem. 2 goes into 150 times, and this will be a -10.1. Maybe just double check. Yeah, that is. And I'm going to say that's -505. Now, you could sit there with a calculator and add those up if you want, but because I know that's an arithmetic summation, in other words, it's the arithmetic sequence that's being added up, I could just use the summation formula. Very, very powerful. So this is going to equal -505. You double check my math if you want. So here we are, we're asked to find the summation. Remember, summation notation, right? Just means that this is going to be 3 plus 0 plus 3 plus 0.25 plus 3 plus 0.25 times 2, and so on and so forth down the line until you get to plus 3 plus 0.25 times 10. So I started with the index of 0 for k, plug that in, and then I incremented to a k equals 1, k equals 2, all the way until k equals 10. That was from our summation notation lecture. And really what you're doing is you're taking a sequence of values, 3 and 3 plus 0.05, basically an arithmetic sequence. This is the arithmetic sequence right here. And you're adding terms of that arithmetic sequence to itself. If you list out the terms, they look like this. A sub 1, actually technically a sub 0, right? So I'll just zoom in. I'll say a sub 0 is equal to 3. A sub 1, I started 0 because they forced me to start at k equals 0. A sub 1 is equal to 3 plus a 0.25. A sub 2 is equal to a 3 plus a 0.25 times 2, and so on and so forth. So I happen to know each time I'm just adding a quarter to get to the next value in line, right? So this is definitely arithmetic. I don't actually need to get too technical into the formula, because if I want to know, hey, I need to add up the first bunch of terms here, then it's a little bit easier just to use my averaging formula. Now remember, the averaging formula said S sub n is equal to n times the average of the first and last term. Well, this is going to be a little bit tricky, but only a little bit. Because really, how many terms are you adding up here? Are you adding 10 terms? Well, count it out loud. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you've just lost fingers, so go to a toe, right? Because you just counted 11 objects. So really you're adding up 11 things here. I don't know if I would write it as S sub 11. I think I will. I'll go ahead and do that. S sub 11. Remember, that goes there. And the first term in this list is a 3. And the last term in this list will be, if I had plugged 10 in there, so 3 plus 2.5 or 5.5. So this is one way to do it. I think a lot of people have a problem when I do it this way, so I will show you a different way as well. But this is actually, I think, the most ideal way of dealing with this problem, because you don't want to just adhere to a formula memorized. You don't want to just say, well, the formula says this. You want to be able to kind of bob and weave if you need to. The sum of the first 11 terms of an arithmetic series is going to be 11 times the average of the first and last term in that arithmetic sequence. If I said series, I meant sequence. Okay. So the sum of those 11 terms is 11 times the average of the first term in the series when k was 0, and the last, I meant to say sequence, and the last term in the sequence when k is 10. And I think that's pretty good. So let's go ahead and just finish this out. This is 11 times, let's see, 8.5 divided by 2. Well, that's no fun. So I'm going to go ahead and compute that out very, very, very quickly. 11 times 8.5 divided by 2 is 46.75. That is the sum that you're seeing right here in the summation. Very fast way to do it, because we knew that the sequence that summation is working upon is actually arithmetic. It started at 3, then went to 3 1/4, then went to 3 2/4, then went to 3 3/4, and so on and so forth down the line, each time adding a quarter. I highly recommend that you get used to that summation formula in terms of the average of the first and the last in the sequence you're considering. That doesn't mean that you need to throw out the other part of that theorem, the first formula. It's just that I think it's much easier to remember this one. And if you have questions on this, ask them in the comments. I do reply to my YouTube comments. Well, the ones that aren't dirty. So an arithmetic sequence has the first term a sub 1 equals 1. Right when they say that, I'm just going to say, okay, so therefore a sub n is equal to some common difference n minus 1 plus 1. Okay. The fourth term is 16. Right when they tell me that, I'm just going to say, okay, well, let's see, I can find the common difference by computing the slope, right? So the common difference is going to be the slope between those 2 points. 16 minus 1 over 4 minus 1, which is 15 over 3, which is 5. So I immediately know the formula. I didn't really have to do very much for that. How many terms must be added? So that the sequence sums to 2,356. So what is n so that s sub n is equal to 2356? Well, remember, the sum of the first n arguments is going to be n times the average of the first argument, or the first term in your sequence, which is 1, and the nth term in your sequence, which we don't know, all over 2, right? It's the average. And we want that to be 2356. Now, this is pretty apropos, because I had just said the other formula you'll probably want to use every once in a while, and here's where it occurs. Although you don't actually have to memorize the other formula, you could just say, great, the sum of the first n terms is n times the average of the first and last term, the first and the nth term in your sequence. Well, we don't know what the nth term in the sequence is, but we sure do have a formula for it. The formula is written right here. So I'll just replace that a sub n with a 5 n minus 1 plus 1. And that's all still over 2. And we want that to be 2,356. Look at the unknowns in this problem. Just a couple n's here. I'm going to multiply both sides by 2 to get rid of that fraction. And I'm also going to clean up the interior of this. This is 5n minus 5 plus 2, or minus 3. Let me just double check. 5n minus 5, but plus 2 is minus 3. Great. And I'm multiplying both sides by 2. That's 46, 47, 12. Now you should note this is going to be quadratic. This is 5n squared minus 3n minus 4,712 is equal to 0. Now, I don't know about you, but I don't know two numbers that multiply to 4,712, which add with 5 somehow to get to a -3. So I am going to go ahead and use Pythagorean or quadratic formula here. because, well, I'll spend more time trying to factor this than I will just using the quadratic formula. If you haven't watched my videos on factoring and solving quadratic equations, my advice is always to try to factor for the first 20 seconds. If you can't factor it in 20 seconds, then move on and use the quadratic formula. I immediately know it's going to take me more than 20 seconds to try to factor this, so I'll just use quadratic formula. N is going to be the opposite of that 3, which is 3 plus or minus the square root of 3 squared minus 4 times 5 times negative 4,712 all over 2 times 5. It's pretty messy. That's why I have a calculator right next to me. So I'm going to go ahead and quickly compute that. That's going to be 9 plus 20 times 4712. I get the square root. This is equal to 3 plus or minus square root of 94,249. Now, I know one of you knows the square root of 94,249 offhand, but I sure don't. So I'm just going to go ahead and take the square root of that answer. It's 307. So it's 3 plus or minus 307 divided by 10. Remember what n stands for. It's the index of your arithmetic sequence. N is 1, 2, 3, 4, 5, right? So it's an integer, it's positive specifically, so it's a natural number. So I'm not going to go for the negative there, because the negative on that will force that number to be negative. I will add. I'll get 310 over 10, which is 31. So going back and seeing what this means in the original question, how many terms must be added so that the sequence sums to 2,356? Oh, well, 31. 31 terms must be added. Again, I'm just using the averaging formula for S sub n. And then in this case, the averaging formula didn't really quite help out, but it sort of did, because it was the average of the first and the last term. We just didn't know what the last term was, but I have a formula for it in blue. All right, just when you thought it was all done, one last question. The last question I have is going to be actually an application, a really cool application. There's a lot of different applications with arithmetic sequences, by the way, and summations of them. This is just one of them. An architect designs a theater, a movie theater, whatever it is, right? With 15 seats in the first row. So here's the first row, it has 15 seats. And then 18 in the second row. And 21 in the third row. That makes sense, because theaters kind of widen out as you go up in the rows. So if the theater is to have a seating capacity of 870, how many rows must the architect use in their design? So I want to know, if we want all of these rows to add up to 870, how many rows? Well, you're actually looking at an arithmetic sequence representing the number of seats per row. Row 1 has 15 seats. Row 2 has 18 seats. Row 3 has 21 seats, and so on and so forth. Notice every row just adds 3 more seats. So this is arithmetic with a common difference of 3. A sub n in general is going to be 3 times n minus 1 plus 15, right? Common difference times n minus 1 plus the initial row, basically. And we want to find out how many rows do we have if we have 870 seats. So I want the sum of all of those seats to be 870. That's what I want. Well, the formula for S sub n is n times the average of the first term in the sequence plus the last term in the sequence, the nth term, I should say. So we kind of need to know how many terms. We need to know what a sub n is. Luckily, we have it. This is literally the last problem we did. Well, not literally, because it's not the same exact problem, but whatever. So multiplying both sides by 2, I get the following. 16, 17, 40. You'll hear me speak my math, by the way. That's when I say 16, 17, 40, that's me performing the mathematics. 2 times 800 is 1600, and then I'm 2 times 70 is 140. So it's 16, 17, and then 40. That's just how I do it. Anyhow, but a sub n we know a formula for. It is 3 times n minus 1 plus 15. And we're back down to the, again, like I said, the previous problem. You're just solving a quadratic equation. So this would be what? N times 3n minus 3 but plus 30, so plus 27 is equal to 1740. And I'll distribute through, that's 3n squared plus 27 minus 1740. Now, I told you in the last problem that I really don't waste time factoring if it's ridiculous. If I look at this and go, oh, I don't want to waste time factoring. But one thing I can tell you here is all these numbers are divisible by 3. 3 is divisible by 3, obviously. 27 is divisible by 3, again, somewhat obviously. And 1740 is also divisible by 3 because its digits add to a number that's divisible by 3. So anyhow, I'm going to rewrite this as n squared plus 9. Oops, n. That's what that was supposed to be. N squared plus 9n minus, I actually used a calculator for this. Don't think that I'm a human calculator. 580. Now you might be able to actually factor that very quickly. In fact, maybe I'll try. I'll give myself a few seconds here. 29 and 20 actually does work out. So n, let's see, plus 29 and n minus 20. Let's see. Yep, that'll work. So we have two choices, n equals negative 29 or n equals 20. We obviously know it's going to be n equals 20. So what does this mean in this situation? It means that we get 20 rows in this theater. That's actually not too bad. A 20 row theater, that's okay. And that will give us 870 seats. So how many rows? 20 rows. If you're wondering how I factored so quickly, I kind of cheated a little bit. I sat there and thought, okay, it's got to be two numbers close to each other. So I started with 25, 580 divided by 25. And then I started working my way actually upwards. I went 580 divided by 26, then 27, 28, and then 29 gave me a result of 20. And the difference of those two is 9. So that worked out for me. There you go. All right. So that actually ends Arithmetic Sequences. Kind of a longer video. I apologize for that. But well worth it. Arithmetic sequences are pretty darned awesome.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.